Yes, so finally we are in session 4. Thanks, Georg. Thanks, Agnes. And I'm very honored to introduce or to announce that we will have the invited talk by Corey Inkman from Microsoft Research now. She will talk about when humans and AI collide, and I think that this is a really, really nice talk fitting into the context of also the papers that we have afterwards. So let's take a look at the talk.
Hi, my name is Corey Inkman, and I'm excited to be participating in IAL 2020. While I'm disappointed that you were not able to be together physically, I'm excited to be here virtually to share with you some of the work that we've been doing related to systems that complement human and AI strengths. Today, my talk is about what happens when humans and AI collide, when my insights or opinions conflict with the insights from the AI. So my research background is in human-computer interaction, and I spent over 20 years studying ways to support rich social interactions with video technology. Ironically, if I could have anticipated a world pandemic would hit and everyone would need to mediate their work and social lives over a video, it might have made sense to continue that research direction. But I had already found a new passion, and I'm excited to share that with you today. So as the use of AI systems in society began to take off, there were many researchers at MSR looking at social issues of AI. I attended many talks and was particularly interested in the talks related to bias and fairness in AI. Many of these talks would start out the same way. They describe how people and society are biased, which in turn causes our machine learning systems to be biased. And then the speaker would spend the rest of the talk describing ways we could fix the algorithm or debias it. As an HCI researcher, I always wanted to stop the speaker and ask, well, what about the human? What about the ways people interact with those systems? Don't those things matter? Did anyone even talk to the users? I recognized there could be strong benefit to having more HCI researchers working alongside AI researchers studying human AI systems. So this led me to shift my research away from human collaboration to look more closely at human AI collaboration. Building great human AI systems isn't just about great AI. The human is a critical part of the process, and it's important that we study the interactions of humans that use the AI systems or that interact with the AI systems. Figuring out how humans and AI can work together effectively is complex, and it's something that we've only just scratched the surface of. Today, I want to share with you a few important learnings that we've made in this space so you can better understand the importance of HCI research, the type of problems we are studying, and the impact we are striving for. There's 4 key takeaways I hope you will get from this talk. First, AI needs to be studied in the real world. Second, the goal many times should be human-AI complementarity. Third, the best AI is not always the best AI. And fourth, it's critical to understand both human and AI bias in the interaction between these two. So my first takeaway shouldn't come as any surprise to this audience. AI needs to be studied in the real world. The real world is messy and complex, but we need to understand how our systems work in these less than ideal environments. For example, AI systems have been used in the criminal justice field to predict recidivism and bail decisions. But when they were then deployed in the real world, they were shown to have strong racial biases. But what about the medical domain? Surely AI systems can help there. Yes, but again, the medical field is incredibly complex and the stakes are very high. Many doctors don't trust AI systems and feel they're not ready to be used in the real world. And what about something like self-driving cars? AI is definitely going to make self-driving cars a reality, and they'll probably be better than the average driver. But what if they keep crashing into things? Or even worse, what if they accidentally kill someone? Are we okay with that? When we explore how AI systems are used in the real world, we realize that humans impact many stages of the AI pipeline. from contributing to training data, to building models, to actually interacting with the system itself in the real world. And in all of these instances, human and societal bias can impact the resulting outcome. So what we need to care about is not necessarily the performance of the AI system itself, it's the team performance of the human and the algorithms working together. So any study of AI needs to think carefully about the people in the workflow, the context surrounding the use of the system, and the potential societal implications. So my second takeaway is that the goal should be human-AI complementarity. So what do I mean by human-AI complementarity? Well, basically, it just means that we should be building systems such that the human and the AI complement each other's strengths and weaknesses. For example, in many cases, the AI and the human have complementary knowledge and skill sets. There are things that the AI system knows and can process that the human has no hope of comprehending. Additionally, there are things that the human knows and can reason about that's very complex for the AI system to understand. And there's things that both the human and the AI know, and the amount of overlap in these three systems depends on any given scenario. Let's look at a few examples where humans have insights that are critical to the problem that may be unaware in the AI system. So for example, in the criminal justice field, the AI system can analyze decades worth of data, can uncover patterns that would otherwise go unnoticed. However, the judge has access to the defendant. The judge can talk to, ask questions of, and listen to the defendant. They can also learn from their rich personal experiences. This undoubtedly means that the AI and the judge have access to similar but different information. The same can be said for the medical domain. AI systems can analyze huge amounts of data and extrapolate from learned insights. But the doctor has access to the patient and can understand the patient's needs and desires. Real estate is another example that we can all relate to. While there's many AI prediction systems that can come up for estimates with how much my house is worth, we also understand that these systems have never stepped foot in my house, and they can't understand the level of upgrades that I've done or haven't done in my home. It doesn't mean that these estimates are worthless, but they're incomplete, and they require insights from experts to adapt them to be more accurate. So let's take a closer look at human-AI complementarity in a real data set in the criminal justice field. So back in 2018, researchers from Dartmouth College examined performance of mechanical Turk workers on a recidivism task. The goal of this work was to assess how well these naive users could predict recidivism compared to a commercial AI system. So the screenshot here shows the task that was given to the mechanical Turk worker. They were given a description of the defendant and then asked to predict whether they thought that defendant would commit a crime in the next 2 years. The results were striking. The mechanical Turk workers had similar accuracy to the commercial AI system. Both were approximately 65% accurate. Now, when we saw this result, one of the things that we were curious about was, were Compass and the mechanical Turk workers getting the same 65% correct? Were there models of who might recidivate and who might not very similar? And this would be represented by the Venn diagram on the left. Or were the mechanical Turk workers and the AI system performing differently, with some level of overlap and agreement, but also cases where they disagreed? And this would be illustrated by the Venn diagram on the right. When we looked at the data, it revealed that 50% of the time, Compass, which was the AI system in this data set, and the humans were in agreement and they were correct. For the other 50% of the time, the performance was split into thirds. 1/3 of the time, both the AI system and the human were in agreement regarding their predictions, but unfortunately they were both wrong. And this is represented by the red slice in this pie, and it sort of represents the unknown unknowns. The remaining 2/3 represent the instances where the human and the AI disagree with each other. And 1/3 of the time, Compass was correct, which was the AI system, while the human was wrong, and the other third of the time, the human was correct and the AI system was wrong. So this space of disagreement represents the potential improvement we could make in the system if there was a way to determine which prediction should be chosen. So one approach we tried was to train an additional hybrid model to determine which prediction should be used, the human or the AI. We looked at all the different features in the system as well as the predictions. While our hybrid model did show some improvement, the result wasn't definitive. So understanding and trying to resolve this issue of what to do when the human and the AI disagree is still an open research question we are exploring. If I disagree with the AI, how do I know whether I'm right and the AI missed something, or the AI has discovered something that I didn't know and it's correct? How do I know whether to accept insights from the AI or overrule it? And does it matter my level of expertise or authority, whether I'm a doctor or a judge, or a social worker or a loans clerk? These are all important questions to be looked at. Additionally, looking at prior work in this space, in general, humans are not good at critically assessing their own performance and often have trouble determining when they should accept a recommendation from an AI system versus overrule it. But part of this problem lies in the fact of how we're designing some of these systems. The AI insights are often just handed to a user, and the responsibility lies completely on the user as to whether they should act on it or not. And even if an explanation is given for the recommendation, there's no support for dialogue with the system and often very little support for interaction. So there's no opportunity for me to question the AI or the AI to question me. So we can try to understand where our disagreement is stemming from, or for us to discuss our opposing viewpoints and try to come to some sort of common ground. I believe we need to explore systems that help support this process of human reasoning to better support human AI decision-making. So my third takeaway is that the best AI is not always the best AI. So this is kind of confusing. Shouldn't I be trying to build the best or most accurate AI system I can? Well, not necessarily. If our goal is human AI complementarity, the best AI may not result in the best human AI system. Let me explain. Today, many human AI systems are built without any regard for the strengths or weaknesses of the human. The AI system is optimized and the result given to the human. Sometimes this approach helps human performance, and another time it degrades human performance. And most of the research in this space has shown that even with improvements, human performance often doesn't rise to the level of the AI. So this isn't really what we're striving for. What if we instead develop the AI system to leverage the strengths and the weaknesses of the human? So for example, last summer, there was a project at Microsoft Research that used the Chameleon 16 data set to explore issues around human AI complementarity. Chameleon 16 is a data set assessing whether breast cancer has reached lymph nodes based on imaging scans. Using a tool developed at Microsoft Research, the researchers ran an error analysis of the human performance on this task to better understand when are humans making mistakes and whether or not there was structure to their errors. And what they found was that, yes, there was structure to the error the humans were making. Overall, their average error rate was 8%. But as we can see in this error analysis graph, examining just 2 features accounted for 57% of the human error. Unfortunately, even though we know this, with the current practice of integration, there's a lost opportunity. The training of the machine learning model has no idea what regions the humans are struggling with, and therefore did nothing to try to complement the human in these areas. This resulted in a model that was good where the human was good and bad where the human was bad, which wasn't overly helpful. We instead created a joint optimization framework for learning the predictive model in an aggregator, such that the framework not only optimized for getting the ground truth right, but it learned what the human was good or bad at, and the whole framework is optimized for team performance. As a result, we get the complementary behavior from the machine learning system. The model is strong in the areas where the human is weak, and the model knows when to ask for help in regions where it has uncertainty, but the human is strong. And this is how we can leverage human AI complementarity. So my fourth takeaway relates to the need to understand both human and AI bias. Almost every day, the news reports some sort of instance where an AI system demonstrates bias. For example, a few weeks ago, there was a report about a machine learning tool that can fill in missing pixels for a low-resolution photo. But as we can see here, even for a highly photographed, iconic image, this result fails. Here, Barack Obama is digitally enhanced in such a way that he now appears to be a white male. The dangers of algorithmic bias have been widely explained and remain an open research area today. Any AI system that is built for the real world needs to be closely examined for potential bias. While algorithmic bias is a common discussion topic, we also need to remember that human bias is also important in human AI systems. And we need to ensure that we examine all potential sources of bias in human AI systems. So what are the implications of human and AI bias in these real-world systems? So first, AI bias is not the only factors we need to worry about. In many domains, humans bring their biases, and they sometimes can be much harder to quantify. Second, what matters at the end is not whether the AI system has biases. It's how having AI in the loop affects the team biases or the resulting outcomes. Third, there's also an opportunity here that we can learn about human biases and potentially use AI as a tool to overcome these existing biases. So let's take a look at an example of a human AI system in the real world, such as hiring. So even without an AI system, hiring is a complex workflow with several sources of bias or error. On the left, we see there's world and societal bias that impacts the candidate pool for any given job. And on the right, we see that there's human bias in the selection of the candidates and the hiring recommendations. When we add an AI system to this workflow, there's now an additional area of potential bias, the screening algorithm that produces a candidate slate for the human. An attempt to mitigate bias that may be introduced by screening algorithms, LinkedIn uses a process called representational ranking to ensure that the resulting slate it presents to humans has a similar distribution to the candidate pool. So what they will do here is they will look at the distribution of a sensitive variable, like gender, in the candidate pool, and then they will ensure that their screening algorithm produces a candidate slate that has a similar distribution to what is in the candidate pool. So while this may help ensure that the screening algorithm is not introducing new biases, it doesn't do anything to overcome the inherent societal and human biases that are already in the system. So we wanted to better understand whether representational ranking works and whether it can be used to help mitigate societal biases. So we looked at several different professions, many of which have gender biases, and examined what happens when we provide users with a balanced slate instead of a skewed slate. So for example, this graph here shows that some professions like nannies and elementary teachers are heavily skewed towards female candidates. And others like orthopedic surgeons and plumbers are heavily skewed in society towards male candidates. And so in these cases, we wanted to look at what happens, particularly in these heavily skewed distributions, what would happen if users were presented with a balanced slate of men versus women. Well, what we see that in many cases, presenting a balanced slate helped mitigate the bias that we were seeing. So we see in the percentage of females in the real world were heavily skewed, either very low or very high, but the resulting selection of females decisions were relatively balanced. So again, in these cases, we're seeing that presenting users with a balanced slate helped mitigate the gender bias in the resulting selections. However, there were other cases that when even providing a balanced slate was not enough and the gender skew remained. We see that for some of these cases, urologist and nanny, even though there was still a bias in the resulting slate, the bias was reduced by presenting the balanced slate. But for the other professions, particularly OBGYN, which is a heavily gendered profession, we see that even though we provided a balanced slate, there was still an increase in the bias in the resulting sample. So this study shows that in some instances, we can use algorithms to help mitigate human or societal bias, but further research is needed to understand in what instances this helps or hurts. So while we saw that an algorithm can help mitigate human bias, what happens when the AI itself is biased? Does that bias cause the human to be biased? Or does it increase the bias in a human? How does the interaction between human bias and machine bias play out? For this example, I'm going to discuss a profession selection task, which is also part of a hiring workflow. In order to recommend candidates, a system has to be able to accurately identify the profession of a prospective candidate. For example, if you walked into this room, who would you guess were the doctors and who would you guess were the nurses? Would the gender, age, or race play a factor in your prediction? We designed a mechanical Turk task to represent this profession selection task. In this task, the user is provided with 8 real-world bios and asked to identify which 4 they felt matched the target profession. We examined 3 different pairs of professions that are frequently confused: attorney paralegal, physician surgeon, and teacher professor. As we see in this example here, the mechanical Turk worker is asked to select which of the bios are teachers. And so 4 of the bios are teachers and 4 of them are professors. In some cases, the human did this task on their own, and in other cases, they received an AI recommendation to assist with the task. And so in this case, we can see that the AI has recommended that the second bio is a teacher, but is not recommending that the first and third bios are teachers. So we looked at 3 different agents in this study. A random agent, which basically makes recommendations via a coin toss. We also trained 2 different types of models. One was a bag of words model, which assessed the words in the bio to help predict the profession. The third model was a deep neural network. Looking at the accuracy of these 3 agents, we see that the humans perform slightly better than random, but the bag of words model and the DNN models both significantly outperform the human. We then examined the user's performance when they were provided with a recommendation from one of the models. We see that the random model did not alter the human's performance. This is useful as it shows that the user was able to recognize that this model performed poorly and its recommendations did not deter from the human's performance. Both the bag of words recommendations and the DNN recommendations significantly increased the human's performance. However, it was still below that of the AI recommendation on its own. We next examined whether or not there appeared to be any gender bias in the predictions. For humans, there was a slight bias towards assuming that female candidates were paralegals and not attorneys. There was also a slight bias towards assuming that female candidates were teachers and not professors. For the random model, there was no observed bias, which makes sense given the design of the model. For the bag of words model, there was also a bias towards assuming that a female candidate was a paralegal, not an attorney. And there was also a bias towards assuming that a male candidate was a surgeon, not a physician. The DNN model exhibited 3 biases: assuming that a female candidate was a paralegal or a physician, and that a male candidate was a surgeon. So what happens when we combine these biases when the user is taking a recommendation from one of the AI systems? In the case of selecting the paralegals, given that the bag of words model was also biased, the resulting recommendation actually ended up increasing the level of bias in these selections. When selecting surgeons, the human was initially not biased, but when they received the bias bag of words recommendation, it actually caused them to be biased towards selecting the male candidates. So in this case for surgeons, we see that the bag of words model induced a bias that didn't exist initially with the humans. And finally, when selecting teachers, even though the humans exhibited bias towards female candidates, the recommendations from the unbiased bag of words model related to teachers meant that the user's bias was mitigated and there was no resulting bias in the choices. So overall, the bag of words model was problematic, as we saw cases where it induced or increased bias when it itself was biased. Now here's where it gets interesting. The DNN model had the opposite effect. So even though the human had biases and the DNN had biases, when the human was given recommendations by the DNN model, its recommendations seemed to mitigate the bias in the human. In all of the human plus DNN recommendations, they didn't exhibit any gender bias in the results. So this is really encouraging. So what's contributing to this effect? One of the things we looked at was the level of conformity with each model. So if a user did the task multiple times, they were paired with the same agent every time. So if I did the task the first time with the bag of words model, in subsequent trials, I also used the bag of words model. So in this case, regardless of the model I was given, the user interface was exactly the same, didn't look any different. But what we see over time is users' trust in the bag of words model appears to be growing, and over time they're conforming to the recommendations from the bag of words model. However, this is not the case for the random model or the DNN model. So the different models cause users to interact with the systems differently, and that also impacted the bias propagation in the human AI system. So our hypothesis as to why this was happening, again, because the interface that users were given was identical and it didn't look any different on the surface. But what we think is happening is the bag of words model is using a linguistic approach to solving this problem. And it's probably very similar to how the humans are approaching the task as well. So when they receive the recommendation from the bag of words model, they're intuitive, they kind of make sense to them, so they're more likely to conform to them. In contrast, the deep neural network model, the recommendations are not as intuitive to the user, so they're less likely to conform with them. However, they do still seem to help. They still do improve the error rate of the human selection. And they do help mitigate bias. So there's something about them that are making the user think more carefully about their choices in such a way that the bias is mitigating. So this is a fascinating result, which we hope to investigate and dig into deeper in the future. So I'm going to wrap up here. So in summary, what happens when human and AI insights collide? Well, it depends. It depends on whether the system was designed to handle the complexity and uncertainty of the real world. It depends on whether the system has been designed to leverage human-AI complementarity, and it depends on whether human and AI bias are understood and mitigated. So in closing, I hope that the examples and the insights I have shared have inspired you to explore human AI systems and to help understand how we can build complementary systems that harness the strengths of both humans and AI and can have a significant impact in the real world and also help mitigate bias. Thank you for attending my talk, and I would also like to acknowledge my collaborators who contributed to the work I shared with you today. Thank you.
Thank you very much, Corey, for this interesting talk. Are there any questions in the audience? There's no question in the Q&A until now, so you can write your questions into the Q&A window from Zoom to ask questions, or you can just raise your hand. And I saw that some new people came in during the talk, so the talk is also available on Slides Live. So if you missed the beginning, feel free to watch it on Slides Live again. Slides Live again. Yeah, so other questions? I see that Vincent does have a question. So then let's start with Vincent.
Okay, thank you, Corey, for this. That was a very interesting talk. I have a question about the way that the data are collected. There is two ways to collect the data, and most of the case, the data are, you mentioned, are observational. That means that they are not created for particular tasks. They are not controlled data set. Did you observe the difference in the results between observational data and controlled data set?
Thanks, Vincent. That's a great question. Most of the work that I've shown has actually been working on observational data, which makes it really challenging. For example, like the recidivism data set, the ground truth there is whether or not the person commits a crime in the future. But as we can imagine, at the point in time when the decision is made, you might have made the exact right decision, and the ground truth is different because of external factors that may have happened over the 2 years. And so the ground truth in many of these data sets in the real world are really messy. And so it makes it much more challenging than if we had a very sort of controlled data set.
Yes, thank you. The next question is from Andreas. So Andreas, feel free to ask your question.
Okay, should be unmuted now.
Yes, it's working.
Hello, so thanks for the great talk. Now I have a question regarding, because we've done research, say, in the same field of connecting humans and machine learning models. And one problem we found actually threatening was what I called the risk of manual overfitting. So when the user is in the loop, say, for example, the user can label data, the user can select or deselect features or data points. So what can happen is that actually the model's actually well, been driven into overfitting. Now this is obviously avoided with, or people try to avoid it in machine learning models with some regularization terms. And I was just wondering, what are your thoughts on that? Should we constrain the users by putting some sort of regularization as well on the user action?
Yeah, that's a great question. And unfortunately, I don't know that I have a great answer for it yet. Because again, I think this relates to the complexity in this space in terms of, I mean, there's so many things that that we see when users are interacting with recommendations. Even studying it, if I get the recommendation from the AI up front, does that bias me one way? If I wait and get the recommendation later, then I probably have some bias towards, some anchoring bias towards my original decisions. And so I think this issue of how users make sense of the models and whether or not they choose to adapt them or overrule them or go with them is, there's just so many factors in here that that we don't know enough about yet. And so it's an open area of study. We have a study going on this summer where we're looking at this, trying to also get data from expert users interacting with these types of systems. And so we have real estate agents that are going to take an incomplete AI model that's predicting the housing price and have them try to augment it with their expertise. But we haven't finished running the study yet, so we don't know how well that's going to work or not. But it's a really important issue in this space.
Okay, thank you.
Thanks. Are there more questions? I think the easiest way is just to raise your hand. So not like this, but in the Zoom app. Yeah, there is another question by Fernanda Silva.
Hi.
Yeah, hello. What is your question?
Hello. Hi. Thank you for the talk. It was great. And so I'd like to ask you about, because there are a lot of research and ongoing work on explainable AI, like to try to explain what the model have predicted or recommended. And do you have any work that says for the end user if this is valid, if the user has understood the explanation of the model? So because usually we only evaluated this kind of approach with developers or data science. What about end users?
Yeah. So as an HCI researcher, I'm super excited to see all of the work that's going on in the explainable AI community, because that is critical for the end users to be able to understand what the system may or may not be doing. And there's lots of researchers that have looked at whether or not the explanations help or hurt, and we're seeing a real mixture. I think one of the challenges I've seen in a lot of these studies is a lot of times they're dealing with novice users, like Mechanical Turk population. And from what I've seen from some of our work, if you look at novice users versus expert users, the results are very, very different. So I think explainable AI is going to be critical because of what I mentioned in the talk. I tend to view human AI collaboration as if the AI is another collaborator that is sort of a heterogeneous collaboration. And so what I need to be able to do is not only understand what the model may be doing, but we need to have this back and forth to help establish common ground. Because I need to, at some point, not only understand what the model may be doing, but in this particular instance, should I trust the model or should I trust myself when we disagree? And it's a space of disagreement that I think is really challenging. And so I think we need to see more work in the explainable AI community. It's more than just, hey, here's how I came up with this recommendation, but also helps reflect on the differences that the human may have. So if you think about this from the perspective of if two human experts were talking about it, if you gave me a recommendation and I disagreed with it, I would pose questions to you and you would explain those additional things. And then you might ask questions about things that you disagreed with my thinking. And again, this process of human reasoning and common ground is where I would love to see this explainable AI community move to, because I think it needs to be a lot richer in these complex domains.
Thank you. It makes a lot of sense, especially because of the interaction. I just remember about the interaction with bots, and it's something that I think it's already missing yet, because the interaction is not does not have a flow. It's more like a question and just one answer, and you have to begin again. So yeah, it makes sense.
Thanks. Yeah, the other thing, as I mentioned in the talk, we had that one study where humans reacted differently to different model recommendations. So even though the interface was exactly the same, and in some other work that's ongoing right now, we're seeing that models with the same level of accuracy, but tuned differently, have a different impact on the user's interaction with the system. And so I think there's a lot of subtlety here that going forward, we need to understand to be able to build human AI systems that can help produce superior performance to the human or the AI on its own.
Thanks.
Yeah, thank you, Fernanda. Are there more questions? Okay, I also, Georg has a question. Please.
Yes, thanks very much for this very inspiring talk, Corey. One thing triggered some thoughts, that you're saying, okay, depending on how you present information, it might be the human decision maker might decide differently on, and I was thinking that probably one way one could use machine learning and AI is to rephrase texts or other, like for example, applications in such a way that biases that are perceived by a human decision maker, that they would be avoided in the text. But then, of course, that might be, that might have consequences in the sense that we kind of take into account a bias that a human decision maker might have, but we are probably not, let's say, we have to educate the decision maker in such a way that they overcome those biases. But what are your thoughts on using machine learning to, let's say, rephrase, reformulate the data that the human decision maker has, such that they can overcome the biases they might have?
Yeah, this is something I completely agree with your point, and we've brainstormed a lot. We haven't done any specific projects to investigate it yet, but I think that looking at ways to use machine learning to understand the human biases as well as the human strengths and weaknesses can help decide maybe how you explain things. So let's say I have a particular bias, and if the system can recognize that, it may present the explanations to me differently than you, who may have a different set of biases. So I think that's a really interesting area to explore. And then one of the other projects that we worked on was also looking at, it was less related to the bias, but more the strengths and weaknesses, because if you can understand which tasks the human are good at and which the AI are good at, then you can decide which tasks get sent to which system. So whether a human takes the bulk of the task or the AI. And again, by using machine learning to understand the human behavior and how individuals are interacting with the system or making decisions, can help inform how we might design the system differently. Great question.
Thanks.
Thanks. So we have time for one more question. If nobody wants, I will take it. So I also have a question, and that is, so I'm just starting with correcting biases and so on. It's also more from the active learning point of view and in the data space. But from what I know is that lots of algorithms that try to de-bias, for example, gender in the application process or so, they kind of put it in two boxes and then just take the first 10, for example, and then in the other box also the first 10, and that's the final list, so it's de-biased. But in my opinion, the problem is that the system itself did not find the real category for finding the best applicants. Otherwise, the result would not have been biased at the first place. Do you think that this might induce other biases or even reduces the performance of the system also? So what are your thoughts on that? Or are there better approaches to solve this problem? Yes.
So I think this is that this is a complex problem that probably doesn't have sort of a solution. Again, biases in our decision making are there every day, and we all know that our data sets have sort of different sorts of inherent biases in them. And I think it's about understanding all of these different factors. And I sometimes worry that when we talk about that I need to mitigate bias or I need to reduce bias, what I should have mentioned in the talk was that context really matters when you're talking about this, because we often view bias as being a negative. It's the thing we want to get rid of. It's in the system, and I think we want to make the best decisions we can. But there's examples where humans, and in a very human way, will use bias in a good way. And so let's say, Daniel, you were applying to my university, and if we had a machine learning model that said, nope, he doesn't, his grades aren't high enough, he doesn't get in. 100% of the time, it's going to come back with that same answer. I, as a human, may look at your application and see things in there that sort of go beyond the feature set that the machine learning model is taking into account. And I decide to give you the benefit of the doubt. That's a very human quality that we don't want to lose. And this is a little bit, it's almost a bit like reinforcement learning, where like the human is more likely to explore. And so, hey, I'm going to take a chance on Daniel, and we're going to see how he does. But then we want the resulting information to be fed back into the system so that when you succeed and are widely successful, other candidates that come in looking like you in the future. So I think, although often in my talk we talk about mitigating bias, I think it's about sort of understanding this whole workflow and learning from it. At the end of the day, we want to try to make the best decisions that we can and improve on those decisions over time.
Yeah, thanks very much. Okay, there's no other questions. So thank you very much for this great talk. Was a real pleasure. And we go on with the next talk. Thank you, Corey.
Thank you.
Okay, so the next talk is from Andreas, and it will be about VLAT, Visual Interactive Labeling for Anomaly Detection. And also here we start by watching the video, and then we have a Q&A session. So feel free to write your questions into the Q&A box so we can sort it out before.
In this paper, we present visual interactive labeling for anomaly detection. We present a preliminary approach and open research questions. So in anomaly detection problems, the data that is available is very often not labeled or not fully labeled. This leads to the fact that the classification accuracy is not as accurate as in balanced classification problems. So following that, the research question underlying this work is, how can we compensate for the lack of a labeled and representative data set in anomaly detection problems by incorporating human knowledge with the aim to move from an unsupervised setting to a supervised setting? So very briefly, the approach consists of 3 steps, which basically follow the categorization of anomaly detection methods given in this paper here, where we start with an unlabeled data set, or where we have a problem setting with an unlabeled data set. We call that unsupervised anomaly detection, or we can train on a data set with just one class, which we call semi-supervised anomaly detection, or we can move to its supervised anomaly detection, where we train on 2 or potentially more classes. So the approach follows that, and we start with an unlabeled data set with an unsupervised anomaly detection model, and by incorporating the user in an interplay with the model, we iteratively label the data to move from unsupervised to supervised in a stepwise manner. Now, what we present in the paper is a preliminary theoretical approach, and we have a prototype implementation for a simplified problem setting. And we identify interesting open research questions that we briefly discuss in the paper. We argue that while there are statistical or unsupervised machine learning methods for anomaly detection, only a human expert can decide whether a data point is to be considered a true anomaly for a given application. Therefore, it suggests itself to incorporate the user into the process. So the approach of visual interactive labeling for anomaly detection consists of 3 steps, which, starting with an unlabeled, completely unlabeled data set, allows to iteratively move towards using supervised anomaly detection methods by incorporating the user and thereby interactively labeling the data. In the first step, we find initial labels by unsupervised machine learning models, for example, autoencoders, LOF, and so on, which suggest initial labels, and the user confirms or overrules these suggestions. And in addition, the user takes own decisions using interactive visualizations. Now, this is in accordance with the VIAL process. In the second step, the labels are refined. The normal data points identified in step 1 are used to train one-class classifiers, and the user again confirms or overrules suggestions and can take own decisions regarding the labeling. Following that, in the third step of supervised anomaly detection, supervised machine learning models are applied. So we can use common classifiers like ANNs, one-class, support vector machines, random forests, and so on. There's one constraint to be considered, that in anomaly detection, there is a huge higher class imbalance, so that has to be considered by the classifier, or sampling methods have to be used. And again, the user takes the final decision regarding the labeling, and the entire process is iterative. That means the user can navigate between the steps, usually starting with step 1 and moving to step 3, but this can be a process of repetitive navigations. We implemented a prototype for a simplified problem setting for 2-dimensional data sets, and we implemented 1 model type per step. So on the right-hand side, we can see a recording of using that prototype where the user can label data sets, where the user can confirm the suggested labels and mark entire regions as outliers. So we evaluated the prototype with artificial data sets and with data from car repair shops. This evaluation supported the identification of interesting open research questions. So, for example, one research question is what we call the potential disruption caused by subsequent models. So if you have a sequence of different machine learning models, each of them might have different assumptions about what an anomaly is. So some work with densities, others with distances, or with the maximum margin assumption, and so on. So it could be that subsequent models suggest quite different labelings. So possible research directions to avoid that could be to find combinations of models, unsupervised, semi, and supervised models with similar assumptions, or to incorporate knowledge acquired in a previous step, and this knowledge being not just the labels themselves. Another research question is what we call the visualization versus model dilemma. So for data with greater than 2 dimensions, the user presented projected data, but a good projection is not necessarily identically well suited for visualization and for the machine learning model to work on. So it could be that a reduced version of the data set is visualized in order for the user to interact with, and the model might work on the raw input data. But visualizing and classifying different representations of the data can induce undesired effects. So some possible research directions can be found in the paper number 24, where this problem is discussed in general. Another problem is the problem of non-interpretability of the projected space. So depending on the projection method, and the projected space is not easily interpretable. So labeling individual data points is usually possible because, for example, certain projection methods, they preserve the neighborhood between the data points. But marking unpopulated regions that is basically trivial in the original feature space is not that easily feasible in the projected space. On the other side, this is a highly relevant feature because domain experts will know in their input data where invalid regions are, which the model should definitely classify as being an anomaly. So there are several possible ways to address this. For example, to use high-dimensional visualization methods, however that makes the interaction more complex, or to support the user by letting the user select data points and for those show the original data, which works fine for data like images, time series of text that can just be naturally represented in an easy way. But for feature vectors that are high dimensional, it is not as easy to represent them. Then research could be conducted on the interplay of projection methods and interaction facilities. And as a final direction, the user could explore different projections. The latter two have been proposed in previous work. And another possible issue that we identified is what we call the risk of manual overfitting. So with the user having full control of all the class labels, it can occur that the user is tempted to label towards satisfying the models rather than applying domain knowledge. So this could be addressed by, as is done in machine learning, using blind test sets, possibly some sort of cross-validation methods. And we want to point out that these test sets should be really blind test sets, not to be presented to the user even after having labeled the data set. And they ideally shouldn't be used more than once. So another more algorithmic way of addressing that would be the introduction of regularization methods to put constraints on the user actions, to not let the user freely take any action. And that could be some regularization methods as are typically used for regression problems, support vector machines, neural networks, and so on. But they would have to be posed in a different way in order to have them control possible user actions. So summarizing this talk, we implemented a first prototype based on the theoretical framework we propose. And it turned out that indeed the approach is applicable. We tested it for a limited problem setting. However, what we found is that there are several open research questions that are worth to work on. And this is basically our future work. So working on the identified research questions, then generalizing and then finalizing the prototype. And following that, we'd like to conduct a user study to see how well the approach works for a number of different users. So for the references, please refer to the paper. I used the same numbering in these slides as I did in the paper. Thanks for listening and watching the video. Goodbye.
Thank you very much, Andreas. Are there any questions from the audience? So until now, there are no question and answer. So there are no questions in the Q&A box. If you have questions, you can also just raise your hand and then you can speak. So maybe we'll wait a short second. Yeah, Vincent.
Yes, if you want. I have a question, but you mentioned this point in the open research for future works. I think there is a very teeny difference between your step 1 and your step 2. Even if you use LOF for the first step and one class classifier for the second step. And you say maybe the labels which are going to be generated in the step 1 will be in conflict with the one which will be generated in step 2. But in this case, it could be solved by using the same, how can I say that, the same class of classifier. For example, if you use in the step 1 isolation forest, and the second step something which is dedicated for one class using again a forest or a tree, that could be a nice idea to have something which labels are not in conflict, maybe.
Okay,
What do you think about that?
Yes, I got your question or your comment. Yes, so you were referring to should we distinguish between the unsupervised step and the one class step? That's indeed a very valid point. Why we started with the unsupervised setting is actually to overcome the cold start problem where we don't have a single label. But what you pointed out correctly, I agree 100%. There are methods which are, for example, LOF was initially proposed as an unsupervised method. Now this can of course be used as a one-class classifier. So there are methods that just work for both. For, by example, putting a threshold on some sort of anomaly score. So yes, that is a good point. That might connect the first two steps, or it might even be better to merge the two steps. I agree with that.
Thanks also, Vincent. Are there more questions? Okay, then I continue with my question. So in the active learning scenario, it's often a bit of problem that we have like a real object and we have some kind of representation so that we can gather the data. For example, there is maybe a real human applying for a job, but we only have the data to see, or even for images, when we see an image, it is represented by a digital photography or so. And to my opinion, humans are especially good in, for example, when investigating these images, to see, for example, hidden objects and so on. And in your example, you had a two-dimensional feature space as an example. So I understand that. What do you think about using the human capabilities to investigate these, let's say, high-dimensional representations, so very high, but for humans, it's even easier because you can just draw the image on the screen and then it's easily understandable for humans. Do we have an idea how to overcome the problems with this representation space there? And yeah, so we don't have a two-dimensional representation where you can print the similarities, for example. Do we have an idea there how to use it, or do you think that this could be an idea to continue?
Yes, well, there are basically a number of options. I mean, the first thing is obviously if you can come up with a projection method, that could work, but that wouldn't always work. And I've pointed out one, say, research question in the paper where especially in the case of anomaly detection, we have highly unbalanced data, so it might not be a very good projection there if the projection method just preserves a neighborhood. So what we can do is, of course, it depends whether the data can be high dimensional, but yet be easily interpreted, like you mentioned, a picture or text. So in that case, it's just, I believe, a matter of showing this data on demand. But what's going to be more general is having the human basically analyze a high-dimensional space. And yes, there are methods from the field of visual analytics to do that. So that is, of course, a further direction. So actually, I'm working in machine learning and visual analytics, so bringing these two together is definitely worth researching. But independent of saying this, I mean, the visual interactive analysis of high-dimensional data has been, there are many approaches that have been proposed, so it's basically a matter of connecting it to that application of labeling.
Yes, yes, yes. Okay, thanks very much. Are there more questions? So if there's one more, we would have time for one more question. Okay, as this is not the case, thank you very much, Andreas. Very interesting talk. And we will continue with the next one then. Thanks.
Thank you.
Okay, so the next talk will be, I think, that Dimitra is presenting. Yeah, and the talk will be about get a human in the loop, feature engineering via interactive visualizations.
Hi, I'm Dimitra and I will present you a feature engineering scheme with a human in the loop based on dimensionality reduction. Feature engineering is typically a costly manual process in chip manufacturing, the application domain of this work. Here we will see how we can improve this process. Before I present the proposed feature engineering method, I would like to give you some background about IC manufacturing. In our daily life, we use numerous devices with advanced chips. These chips are printed on a silicon plate called wafer with an accuracy of nanometer by a process resembling lithography. Examples of chips heavily used in our daily life are memory chips or logic chips like microprocessors or microcontrollers. ASML provides the tools for the exposure of a pattern on a wafer, which is like a photographic process. Besides lithography, a wafer passes many tools in a fab, such as polishing, deposition, etching tools, and others. This process is executed again and again in layers whose number can be greater than 40. For instance, an advanced logic process could have from 600 to 1000 steps and could take up to 3 months to be produced. Here we see a simplified wafer processing pipeline in a fab, which is repeated for each layer. In order to make sure that the production process is going according to the requirements, we need to do expensive performance measurements on wafers using metrology tools. After having passed all the layers of processing, a wafer is tested for yielding devices. Yield tests check the full functionality of the chip. Then the yielding chips are cut and shipped out. Performance measurements are costly and can be a bottleneck in production, and we typically try to avoid them, and we try to infer them for cheaper and available data. As a result, in most cases, performance measurements are our targets that we try to predict from chip sensor data via machine learning models. In this way, we can have significant cost reductions in the monitoring mechanism for inspect specification quality. Due to the nature of machine learning process, we end up with datasets having given thousands of features with spurious correlations to targets, strong context effects, noise, and redundancies. In this reality, feature engineering is important for accurate machine learning models. Also, interpretability becomes a requirement because it establishes trust against spurious correlations for the model prediction. In IC manufacturing, feature engineering typically requires knowledge on the physics of the process, which cannot be easily obtained by statistical techniques. As a result, feature engineering is a costly process which is performed by domain experts manually. To improve this process, we propose the following feature interactive scheme. In this presentation, we will show that, and also we will show an implemented initial approach in ASML, a web application basically that we implemented. A human expert loads a dataset in our application and interacts with the tool in order to engineer features. User interaction is obtained through informative visualizations, namely visualizations that help the human expert to decide which features to engineer. Before I describe the proposed approach, I would like to present you what type of features we perform. Raw features have offsets, and as a result, machine learning models with raw features show low accuracy. These offsets can be explained by the tool associated with the sensors of the raw measurements. They are the context of the measurement. Unlike features, the context variables, such as tool names, machine settings, timestamps, do not have a direct physical relationship with the target, but they are necessary in order to explain the raw measurements. When context offsets are removed, then we can see the real relationship of the measurement with the targets. These context effects are not stable. They depend on the use case and the process configurations, and it's difficult to identify them reliably in a high-dimensional space. So far, identifying context effects was a costly process for experts. Fortunately, with the appropriate tooling, domain experts can easily identify them. To face context effects, we propose the following feature engineering workflow. A domain expert observes a low-dimensional embedding of the raw features and tries to understand the clustering structure present in it. For example, they understand which context is responsible for the clusters in the embedding. After having understood the structure of the embedding, the expert defines the clusters of the features. This information is used to engineer a new feature which has a normalizing effect from the context. Then, the observed patterns are factored out from the embedding. A new iteration begins with the human observing the new embedding for a new clustering that can be used for a new feature. The interaction ends when, at a given iteration, the embedding shows no more relevant clustering. Here we see a snapshot of the user interface of the developed application for the iterative user interaction. Each iteration consists of 4 steps. In the first step is to select relevant features. An algorithm ranks the most relevant features with respect to the target. Any feature selection can be used here without affecting the user interaction. In this implementation, we use Bayesian regression. The user can see the most relevant features and select the number of them that will be used for the visualization. The selected features are visualized in the main plot using dimensionality reduction techniques. Any dimensionality reduction method could be used. For our datasets, nonlinear methods work better, and in this example we used TSNE. The second step is the exploration of the visualization. The user can choose the context to which the scatter plot is colored. For example, it can be the machine where the wafer has been exposed, or any other context variable. The expert sees what context explains the clustering in the data. To facilitate user exploration in the context variables are ranked according to their mutual information with the clustering as defined by a clustering algorithm. So the user can start exploring the embedding using the context that correlates the most to its structure. We note that the user interaction in this step and this process in general cannot be automated because clustering is an ill-posed problem in the sense that different clustering algorithms or different initialization of the same algorithm often give different results on the same data. Having an expert in the loop makes sure that not only the hidden clustering structure will be properly captured by engineered features, but also that the domain knowledge will be used. As an example of knowledge that an expert can acquire in this phase, we see the context effects which can be explained by the machine chamber settings. In the third step, the user gives the understood clustering as an input to the tool. The clustering observed in the previous step can be added as clustering constraints by the user. In this way, the user engineers a feature by computing the clustering offset per machine chamber settings, namely the average target per cluster. In fact, the new feature is a form of target encoding the machine context variable. In the fourth step, the user continues the exploration in order to discover less dominant context effects. To achieve this, we consider the previously acquired knowledge as prior information, and we factor it out from the embedding using conditional TSNE in this example. Other methods for conditional embeddings can be used, as for example conditional variational autoencoder and uniform manifold approximation. The user can select the context effects to be removed, and multiple selections are possible. In this example, the user will select machine chamber, and the interaction will start again with a new visualization. We now present an evaluation of the proposed feature engineering scheme in a prediction problem where the target is a costly metrology measurement and the features are chip sensor data. We also have the context of the chip measurements. Our target is called overlay, and which measures how accurately layers are aligned on top of each other in the lithography process. If two layers are misaligned, then the printed chip won't function properly. It won't be able to conduct current. Overlay is measured over several positions on a wafer and after each process layer, and it's a time-consuming measurement, and that's a bottleneck in production. This is why we typically would like to predict it. Overlay is a continuous value, and thus we have a regression problem. In this use case, we want to predict the overlay of one of the top layers. Our features are chip sensor measurements from the lithography steps and any overlay measurements from previous layers. We have a dataset with 2,000 wafers. Overlay is measured in 60 points on each wafer, and so in total our dataset has 120,000 data points. After feature selection process, from an initial dataset of 350 features, we have now 30 features. To avoid overfitting, we use 10% of our data for feature engineering and the rest of it for training models. We use UMAP for this use case because it performs faster TSNE, and we have a lot of data. Here we see the first iteration. First, we will describe what a human expert learned by observing the embedding and what kind of features were engineered. Then we will evaluate the impact of the engineered features on overlay predictions. Here we observe the first iteration with our tool, and the data in the plot is colored by wafer ID, which clearly explains most of the clustering structure. So, the first engineered features is the cluster offset. The wafer ID related clustering means that the overlay on a wafer, independently of the layer that have been measured, looks similar. In our dataset, the overlay on a wafer are always taken with respect to the same reference layer. This means that if there is a distortion in the reference layer, it will propagate through stack to all layers above. ASML experts can quickly identify this behavior. So, in this case, experts need to make sure that the initially loaded data contains the metrology measurement of at least one of the previous layers per wafer or the reference layer. As a result, another feature is being engineered, and it's the overlay measurements of a previous layer. In the second iteration, the structure observed in the embedding is obvious for a domain expert who can quickly relate it to overlay. It belongs to 8 different machine settings. Here, the engineered feature is simply the estimated average per settings. The third iteration shows a clustering that is colored per position on a wafer. It is known that the measurements of errors on the edge of the wafer are larger than those in the interior rings of the wafer. This structure, again, it's easy for a domain expert to relate to overlay errors. The engineered feature is just the expected error on each position of the measurement. Here we recap the features that we engineered so far. From the first iteration, the engineered features are the wafer ID offset and the previous layer overlay. From the second iteration, the machine chamber offsets, and from the third iterations, the wafer positions offsets. Now we saw how our interactive scheme can improve prediction capabilities and interpretability of the machine learning models. In order to evaluate the accuracy of our model, we implemented a linear and a non-linear machine learning algorithm, Bayesian regression and random forest. The reported results come from a threefold cross-validation. We see that the more features we engineer, the better the R-square values we obtain. Another key method is that once we have engineered all the features, the result by a linear machine learning model and a non-linear one become comparable. Not only we have a much better accuracy, but also we can now interpret much better the prediction of the results. In IC manufacturing, a field heavily relying on the physics of the process, it is preferred to have an interpretable and less predictive model than a more predictive but not well understood one. In this example, the accuracy that we have obtained, it's not really high, it's 0.6 R-square. Metrology prediction is a very challenging task, and as that result, after a few engineering steps, it's quite good. So, our proposed scheme facilitates experts to engineer features in a structured way, using their domain knowledge. Nevertheless, we still face several challenges in implementing the proposed interactive scheme. First, our methods relies on iterative computations of embeddings, which is time-consuming, so faster algorithms will improve user experience. Secondly, we would like to transfer the learned features from one domain to another. Similar context effects are present in many predictive machine learning settings over different domains within semiconductor industry. The reason is that we typically want to predict performance indicators from sensor measurements associated with some context. Our feature engineering scheme requires costly time from domain experts. Transferring the learned features across domains instead of requesting similar input from experts in different domains will improve its efficiency. Third, domain experts are often unsure of their feedback and they might also be biased. Making our scheme robust to such biases and conflicting inputs is necessary for its successful implementation. We also have a presentation about human-in-the-loop applications in ASML in a talk at the ECML industry track. So thank you for watching this talk, and we can further discuss in our Q&A session. Thank you very much.
Thank you very much, Dimitra, for recording this talk. So, are there any questions? Vincent, awesome. Vincent, that's the first question.
Is between a question and a suggestion. I don't know if you know what co-clustering is. So this is a question.
Yeah. Dimitra is still muted. Maybe you can repeat.
Can you hear me now?
Yes, we can hear you.
Do you know what co-clustering is? Because in your case, if you use co-clustering, it could be very nice for you in the different steps you perform, because you obtain co-cluster which are defined by the same features. And by this way, you can, it's possible to select one of the features which is in the co-cluster. And by this way, you obtain uncorrelated features. This is just a suggestion. Maybe it could be interesting to have a look on co-clustering.
Mm-hmm. Yeah, so your suggestion is to look into co-clustering and see if there's an application for the algorithm? Yes.
Yeah. Yes.
Okay. Do you know about co-clustering, Dimitra? Can you comment on that, or?
No, I haven't heard of it. I hear my.
Okay.
And also,
maybe you can describe it with one sentence to understand.
With one sentence, here that you have a table, and the line of the table is the ID of the wafer, and the column of the table are the features. If you perform a co-clustering, then you obtain a cluster on both dimensions, on wafer and feature. And then you are able to find the wafer which are described by the same feature. And this is exactly the thing that is present in your talk.
Yes.
Wafer with the same behavior.
Yes. I understand. I hear my voice twice.
Okay.
Let me comment on this. I understand this, but this comes after the knowledge that wafer ID is a relevant information. This is not always the case. So, yeah, that's
this is you presented that in your slide because you show us a cluster which was defined by a list of wafer. And this is exactly the thing that the co-clustering is going to perform. It's just a suggestion. And the other point is that in your final results, you show that after the first step, the performances are really better than compared to the baseline. Maybe because at the beginning, your features are very correlated. And when features are very correlated, for regression or decision tree, this is a pity.
That sounds an interesting suggestion. We will try it.
Okay. Thanks, Vincent. So, are there more questions from the audience? You can just raise your hand, and then I can see it. Okay, I have just a short question. It's more about the understanding. So you said that you use some dimensionality reduction, for example, TSNE or the U somewhat. I forgot about the name. And is it correct that then the expert is helping with the clustering, right?
Exactly.
Yeah. And how difficult is it for the experts to work in this reduced space? Because then it's not about features that are maybe interpretable or so, because they are some meta features, so some reduced features. Do you have experience with that?
So clustering, oops, yeah, I hear my voice twice.
I can hear perfectly and all microphones are muted. So
Okay.
I'm sorry.
So it's my issue, that's fine. Clustering in the low dimensional space, it's indeed more challenging. In that case, it was quite easy for the expert because the features were easily identified by coloring the clusters. When the situation becomes more complex, I can imagine that it will be more difficult for the expert to interact with low-dimensional visualization. And indeed, supportive visualizations will be needed to help the domain experts to take a decision there. So this is indeed an open thing for us, and we try more on how to support the expert on clustering. For example, what it's the difference between clusters and these kind of things.
Okay, thanks. Okay, are there more questions? We would have time for one more question, but it does not seem like it. So thanks again, Dimitra, for that talk and for answering our questions.
Thanks for the questions.
Yeah, thanks. Okay, so then let's wrap up the workshop for today. We are really pleased with all the participations, all the presenters that really did a good job recording the videos and so on. So we're really happy. Thanks for Vincent and Georg and Andreas and Adrian. And I hope I did not forget someone. Please help me, Vincent or Georg, if I forgot someone. And we really enjoyed the workshop. So we'll be probably here next year as well, hopefully in real life. But until then, we have to drink the cocktail in the virtual environment area. So if you want, we will be there for at least a few minutes. So if you have feedback or if you want to comment on something, if you have questions, you can just join us there, or you can just write us an email or write down in the chat. We're really open to get feedback on how the workshop was for you. And yeah, we're happy to see you all, hopefully with a real drink next year then. Do you also want to say something, Vincent or Georg?
Well, I would like to thank Daniel and Vincent and Adrian and Andreas, of course. And in particular, Corey, thank you for being our invited speaker in this session.
Yes.
So that was a real pleasure to have you all here. And I hope we see each other now in the virtual after workshops, snacks and drinks. And then in real next year at the fifth interactive adaptive learning workshop. Thanks.
Okay, I have nothing to add. Everything has been said.
Perfect.
Thanks.
So then enjoy
everybody.
the evening or the lunch or wherever you are and whatever you do now. Bye. See you next year.
Okay. Thank you, Georg. Thank you, Daniel. Thank you, Adrian.